Hi, and welcome to our demonstration, mlinspect, a data distribution debugger for machine learning pipelines. I'm Stefan Grafberger, and this joint work with Shuba Gua, Julia Stojanovic, and Sebastian Schelter. Machine learning is increasingly used to automate important decisions in domains like credit and lending, medical diagnosis, and hiring. But automated decision-making can reproduce or amplify existing biases or discrimination. One of these issues is technical bias. For example, pre-processing operations can lead to the under or over-representation of groups in the data. You see this in the image on the right. A lot of people from race 3 get removed. We call this a data distribution bug. In this case, this is because there's a correlation between the county and the race attribute. We recently proposed mlinspect, a Python library to automatically instrument pre-processing operations. While fairness cannot be fully automated, we can assist data scientists with finding and fixing these data distribution bugs and with inspecting their pipelines. Now let's take a look. For our demonstration, we'll use two example pipelines. The first one is from the healthcare domain. To speed things up, we'll quickly paste the source code in. Pipeline is written using pandas and scikit-learn. We start by using pandas to load in some data, do some pre-processing. Then we use scikit-learn to transform the data and train a classifier. Similarly to how we would do it in a Jupyter notebook, we can now just execute the code. Here we see the output. And on the right side, see something like a logical query plan, a directed acyclic graph representation of the pipeline. Consists of operators like a data source, a join, and a group by. As we hover over the operators, see the corresponding source code highlighted on the left. Now on top of the stack, we offer inspections. Inspections can analyze the data flowing through the pipeline at runtime. First one I want to show you can materialize the first three output rows of each DAG node. Now let's execute the pipeline again. And let's look at an interesting operator. Here we have a one-hot encoder, for example, that takes relational data and outputs matrix data. Next inspection I want to show you is the lineage inspection. For example, when our one-hot encoder encounters a value we didn't expect, it's hard to do any kind of debugging. This is because we would normally use the social security number in this example to identify input rows, but it's no longer available at this point of the pipeline. Our lineage helps with that. Now we see these lineage annotations for each row. So how does this work? Let's look at our data source. In the beginning of the pipeline, for each data source, for each row, we generate unique identifiers. Then we forward propagate it through the pipeline. We now look at our join, for example. We see how this forward propagation works. So here, both sides already have this lineage annotation. For each row in the join result, simply need to combine these lineage annotations. Next inspection I want to show you is for data distribution debugging. Can compute histograms for sensitive groups and operator outputs. Now let's select sensitive columns to consider. Operator interesting here is the selection. The output distribution for race can be seen here, and for the age group here. Now, traditionally, this would be hard to compute these histograms, because here we have a projection that removes the race attribute. And it's no longer present in the data here. But thanks to annotation propagation, our inspection can do that. Now, on top of inspection, we offer checks. Checks take the results from inspections and verify constraints on them. Simply execute an assertion. Now let's select sensitive columns again and execute the check. Here we see that it failed, and one of the DAG nodes is highlighted in red. It's this filter by county. So here we see that a lot of people from race 3 get removed. This is because there's a correlation between county and race in our dataset. To fix the issue, we add a new county to a county filter. A lot of people from race 3 live. Now the check no longer fails. If we look at the selection, see that now a lot more people from race 3 are still present in the data after the filter. Next thing I want to show you is the no missing embeddings check. Here we have a word-to-vec transformer that transforms last name into features for our model. Now for rare last names, no embeddings might be available, which can also introduce bias. Let's also select this inspection and re-execute the pipeline. See that the check failed and can look at the operator. And here we see how different last names get transformed to different matrix data rows. Now, for one last name, no embedding was found, the very rare last name. To fix this issue, we'll change the way the vocabulary is built for our word-to-vec model. We re-execute the pipeline, and the check no longer fails. Note that the last name probably isn't something you should use as a feature for your model. So for this example, used a synthetic data set built so we can showcase as many of the complications mlinspect needs to handle as possible. The next example, we use a real-world data set and showcase a real-world data distribution bug.
In this example, we use a well-known dataset known as the adult dataset. It's also sometimes called adult income or census income. It's frequently used in the literature on algorithmic fairness. It includes US Census data from 1994 for 33,000 individuals, including sensitive attributes like sex and race. The task is to predict whether the annual income of an individual exceeds $50,000. Here we load in some data with pandas, perform transformations using scikit-learn, and train a decision tree classifier. Here's what the resulting DAG would look like. After training the model, we really should be evaluating on a held-out dataset rather than on the training set. Let's now uncomment these lines to load in a test set, pre-process, and evaluate. Now mlinspect extracts a second DAG because we load and process the test data separately from the train data. In the healthcare example, we loaded all of the data and pre-processed it together before using scikit-learn's train test split function, whereas in this case, the split has already been made and the two sets saved in separate files. The two distinct DAGs simply reflect that we load the data separately and also apply each step of preprocessing separately throughout the pipeline. So now let's run this no bias check on a couple of the sensitive attributes. The check fails and highlights these two nodes in the DAG. The left side is the train set and the right side is the test set, but it's the same step in the pipeline. It's here where we're calling drop now, which removes all samples that have missing information. It's very common for data scientists to ignore missing values, but in this case it means that a person of Asian Pacific Islander race, or a person in the other category, has more than double the probability of being removed from the dataset in this step than a white person. Instead of dropping all rows with missing values, we could use an imputer to fill in missing values with something that seems plausible. For example, the most frequently occurring value. Missing value imputation can also change the distribution of sensitive classes. Since this transformation is applied to the categorical features education and work class, we should make sure the imputer doesn't introduce bias for these two features. So we add them to the no bias check. This time the check succeeds and none of the nodes of the DAG are highlighted. The structure of the DAG has changed quite a bit due to the way that we changed the pipeline. We can dive into the details to see just how the simple imputer affects the distributions of those two categorical features, education and work class. So here's the node for education. If we go down, here is the distribution change for the education category. Looks like overall, very minor changes, almost invisible to the eye. And if we look at the other node, which is the simple imputer for work class, we can see that, again, very minor changes have happened. The NaN group that used to exist before does not exist after, which makes sense since we filled in those values. Overall, the check finds no issues because the changes are only minor. Normally, this kind of data distribution debugging can be really time-consuming and tedious, but mlinspect lets you quickly check for these common issues without having to modify your pipeline code. In many situations, a data scientist, or maybe the data scientist's boss, wouldn't want a machine learning model to be using race or sex as features in the first place. There are actual legal restrictions on the use of demographic features, such as gender, for automated decision-making. For this reason, we've implemented the No Illegal Features check, which automatically flags that. By default, it looks for names of some common sensitive traits like gender, race, and age, but optionally, a user could add more features to flag. Let's say we add sex and education. Fortunately, in this pipeline, we're not using race or sex in this final column transformer, which means that those features are left out of the training of the model. But because we used age, and now I've added education to be flagged, and we used education in the model, that's why the check fails here. To fix it, we can simply remove age and education from the column transformer. Like this. And that means they'll not be included as features during training. Now when we re-execute the check, it succeeds.
Now onto some technical details. Why is building these sort of inspections for machine learning pipelines hard? In relational databases, we have the relational algebra, and we define lots of things like value optimization on top of them. We also already know exactly how to compute different types of provenance, for example, Y provenance. In machine learning pipelines, we don't have an abstraction like the relational algebra, and pipelines are built using different libraries like Spark, Pandas, and scikit-learn. Different pipeline stages, different data representation formats are used, like pandas data frames, NumPy arrays, or sparse matrices. mlinspect is built using the observation that libraries like pandas mostly perform relational operations on data frames, and feature transformation pipelines are often built using the estimated transformer abstraction that scikit-learn popularized. The main idea is to use these common abstractions and extract an abstracted representation of the pipeline that makes analysis much easier. This extracted DAG is the basis for our library mlinspect. We We use it to instrument machine learning pre-processing code with custom inspections, as you saw before. For this, we don't require users to change the code in any way. We have a declarative pipeline using pandas and scikit-learn. They can just input their code directly. The image on the top right shows the API. Users only have to specify the pipeline file and which inspections to apply. This image uses all the example checks we saw in the demo earlier. The interface for inspections can be seen in the other image on the right. Inspections get a local view of the current operator and work using these two functions you can see in the interface here. The first one is for inspecting input-output pairs, and the second one is for annotating the DAG node with some result. For inspecting input-output pairs, inspections get information like the kind of the current operator and also an iterator over annotated input-output pairs. They then return an iterator with annotations for the output row. After processing all data flowing through the operator, the second function is used, and the inspections can annotate the DAG node with something. For example, our inspection that we use to detect distribution changes annotates the DAG nodes with histograms of protected groups. The basis for all of this is to allow the propagation of annotations for each row flowing through the pipeline. And we think of mlinspect as a general runtime environment for machine learning pipeline analysis. We allow users to implement their own inspections. We already implemented several inspections and checks ourselves, as you saw in the demo earlier, but I think it's possible to build many different applications on top of it. So how does this work, especially for unmodified programs? Here you can see a rough overview over the different required steps. Start by using the Python parser to get the abstract syntax tree of the pipeline. Then instrument each call and subscript node in the abstract syntax tree as our own callback functions. Here we can see an example. We have the function afunc with these arguments. Then we insert our own function calls around it to get both the input and output of the original function call. As seen before, we also require users to specify the set of inspections to apply in advance before executing the pipeline. Because each inspection we provide only has a constant overhead per input-output processes, the runtime overhead is linear in the number of inspection input records. We then execute the modified AST. Then these callback functions we introduced earlier, after call and before call, get called. mlinspect then delegates these function calls to different backends depending on what function they wrap. The wrapped function, for example, is a pandas merge call. The after call and before call methods get delegated to some pandas backend that's then responsible for executing the inspections for the pandas merge call. After executing the pipeline, we have the inspection results for some function calls. But we want to associate the inspection results with abstract DAG nodes for further analysis. So we still need to extract the DAG. For this, we first extract an intermediate representation, which is a much simpler version of the AST. The variable definitions and the usage are connected. Then we create the DAG from this intermediate representation, connect the inspection results to the DAG operators. All of the source code of mlinspect is open source and available on GitHub. We currently work on adding control flow support and robustness. In the future, we want to implement more backends for more libraries and implement more debugging approaches on top of mlinspect. We also want to help users make sense of the output from mlinspect and to further improve the performance. If you're interested in more details, check out our cited paper. Thank you.